Okay, so I've had a look at your doc here, where you're putting all your. Oh, you can see I'm looking up baby boy names. At the doc here, and the stuff you've recorded, and you seem to have recorded the important stuff. But for the thing that you're talking about, where you want to predict the eclipses because they're quite sharp, we'll need the ephemeris. So luckily in your document you had the link to your objects here, and I could go back to the Kepler page, which is here. Um, and so we have the ephemeris. So we have this time, that's a time, that's 2 million etc. days since Julius Caesar did something or other, visited his mum when he was 21. I don't know. But it's a 0 point, and it's been 2 million, nearly 2.5 million days since that time. And we have the period here. So what that means, so you should put this BJD on your information page you had. So it's going to be interesting for you because it's going to be the time that you find the minima here. I mean, your project is looking at the light curve and then looking at different colors, figuring out what different stars are, which you'll be able to do from both of these because my pattern recognition tells me that the two stars are very different. So you'll be able to see different colors and figure out spectral types and all that kind of stuff. But one of the other things that for some reason amateur astronomers are particularly interested in, less so professional ones, is the time of minima. When does the eclipse happen? If the eclipses, so you have, it's happened this time, and then every 1.5 days it has an eclipse, you can find that the period changes over time, and you'll have this thing called an O minus C diagram, which I hope comes up with a good example, which means that the period changes over time. If it's one of those W UMA ones, it can mean that they're spiraling into each other, so the period is getting quicker and quicker and quicker and quicker until it's such a point that they collide with each other and become one star. So you'll maybe this is one of them. It's fine going for a while and it starts spiraling in to each other. Maybe there's some kind of precession of the orbit and it does some funky thing with the periods. But so there's a lot of work done in the amateur community. You see a lot of stuff in JAVSO about the timing of the eclipses, but I find that less interesting than what you're trying to do. But it's good to know that it exists, and if you write a paper, you should put that stuff in. So, my point being, you should put this ephemeris in because it is interesting. It's an interesting thing for people to know about. So, if you have this value here, this is the timing of one eclipse. This is it's not an arbitrary number. It's a particular time that Kepler saw a particular eclipse. So it's not arbitrary as such. It is during the time of the Kepler mission. So we have the value. And then we have the period. So the eclipse happens every one of these days. And these errors, we can talk about errors at a different time. So we have, where am I going to put this? Period is this. Okay. So you're going to have to see a primary eclipse here, but then you're also going to see it plus to do it. Oop, no. What have I done? Okay, I want to click there, and then to make it an absolute reference, which means it'll always point to there, I'm going to put some dollar signs around it. Voila. And you can adjust the number of decimal places here. Usually something fishy is going on. Anyway, voila. So this will tell you each time the eclipse happens, because you just keep on adding the period on. So this should be when the eclipse happens all the time. Now, one interesting thing about Excel is it stores date and time in days itself. So what we need to do, which would be, it'd be lovely if LCO worked in Julian days, inputting your stuff, but it works in the calendar. So I haven't done this before. I'm just going to go convert Julian day to calendar date, and there should be all sorts of applets here using Excel. No, I don't want to use that. I want to find just some rough thing I could type some things in and get the actual date up. This looks a bit clunky, but it'll do. So we'll be able to paste in our Julian date here. Let's go that. We'll paste that in. Compute calendar date. Okay, let's see what. Woohoo! Okay, we've got this. Okay, so this is in universal time, which is what LCO works in anyway, so it's all fine. So let's just do some Windows left to get that over there. Get this over here, and there's some private stuff behind you shouldn't be seeing. So scroll that over. So we have November 19th, 2014. That's when Kepler saw that eclipse at that time. So how do we put all that in to Excel? Long date. I really don't actually know how to do this. Give me a second. Okay, I just have to skip out there to figure out how to put in a whole entire date and time into Excel, and you do it by typing in. Now this might be different between US and the rest of the world, because you guys like non-metric stuff. We like metric stuff. We make sense. We make sense by putting the day first, which is the shortest one, then the month, then the year. Now that might be different on your computer, so you better check that out. And then to put the hours and minutes and seconds, we go 09, 52, 49. Okay. Voila. We have it stored in there in Excel. I wonder if it comes out as a number. Yes. Short date. Long date. Surely there's some other way we can represent this. Yeah. Maybe not. And here's where my expertise becomes lacking. Can we put time and date on the same thing? Okay, what I'm going to have to do is go date on one, and then equals this. So convoluted. And then but change the formatting the time. Ugh. So unelegant, but that'll do. Sorry. What I should have done there is gone. So it stores it in days. So to add time to this, we add, there's the original time, plus, and then we do that thing again, because that stores date and time in series of days. That's better. Okay, sorry about that hiccup. And so it will continue to show you when the eclipses are. How you get to 2017 is up to you, really. But I mean, the daft way would be just scroll down a billion times. And then here you can click there, you can press double click on the dot here, that'll scroll down for you, and then double click on the dot here, that'll scroll down for you, and then you just scroll down. And so you just find where we're up to in the universe as we are floating around the sun, and the dates are doing something. And you will see that if we go to 18th of May, which is now, my clock, I also have a UTC clock up here because I use telescopes all around the world, so it's good to be in UTC. At 8:44 a.m. If I look on this thing on 18th of July, there will be an eclipse in about, well, less than 12 hours. A couple of hours, less than 12 hours. So here you can see how you would predict future eclipses, because we've just taken the Julian day, used a crappy online calculator to get it into the normal days and time, and kind of fudged Excel to show us what we want. And so here are all the primary eclipses for the next foreseeable future. But if we have a look at, where are we? Here. We've got the primary eclipse, but we have the secondary eclipse. And the secondary eclipse seems, well, it's artificially visually demoted, but it actually should look pretty prominent. But because it's half a phase out, so what it should look like is, let's wait for my computer to turn up. Deep eclipse, small eclipse, deep eclipse, small eclipse. But because you have this diagram, the small eclipse is on the half phase point, and so it just looks like something weird on the edge. But it's actually an eclipse. It's an eclipse, but it's been cut in half. Whoops. Let me try that with a straight thing. Woo! Yeah, it's been cut in half. So the graph you're seeing is this thing at the end, then the deep eclipse, and then this other half of the eclipse. So it's making it look not as special as it should be. And the same with this one. There's a small eclipse, big eclipse, small eclipse. So we'll also have to look at the where secondary eclipse is. So let's go, this is the secondary. Because Excel stores things in days, we want the date again, but we'll want to add half. So we want to be here, but we want to go halfway through the cycle to get to the next eclipse. Times, I'm going to do that trick again. Let's go back up here, click on that, come back down laboriously. It's probably a better way of doing it. It's too late now, nearly there. Put the dollar signs there. So we're adding half a period onto the value there. Voila. And of course, we have to long date. Doot. So this one's on Friday, and then it'll be a very similar thing, except let's see if that magically works okay. So yes, it's kept the absolute reference, and it's just pointing there. So yes, but now we have to change that to time. There we go. So this will give us the values of the secondary eclipse. So now we have primary eclipse timing and the secondary eclipse timing. So you have one on Thursday, 6 a.m., Friday, 12 a.m., Friday, 6 p.m., Saturday, 12. So we have this timing. So you have to play around with Excel. Maybe in the future I could make something that's more straightforward to do that. But that's how I'm doing it. And I'm just flying along on the seat of my pants, showing you what to do from scratch. This is not prepared. This is live science. So if we go back here and we go to LCO, if we go submit observation, and we want, that's going to make a sensible title, but I'm just making a silly one because I'm going to delete it. So, and whatever, Lare, I'm not, all this doesn't matter because I'm just going to show you how to set the cadence. So I just need to fill in a bunch of values. So from now until next week, yep. So cadence, so we want a simple period. Actually, for the first time, it actually matters where our start time is, because we want to start here's where it gets tricky. We don't want to start at the eclipse. So if we look here, we don't want to start there. We don't want to start there. We want to start somewhere here and go to here. Or roughly kind of sample that area and then have it come around and keep on taking images around roughly this area. So you don't want it to start at the eclipse. So how do we do that? We have to sort of have a guesstimate, and you only really need to guesstimate these things when you have an automated telescope to do this stuff for you. How wide is the eclipse? And then start it off beforehand and get it to run through until after. So if we have a look at your diagram here, I might go to the actual page. Did I get that up? Okay, let's go zoom in a little bit. And we only have to rough estimate it. So halfway through is about 0.125, because that's half of 0.25. Half of 1.25 is about 0.6. 0.06, I mean. 0.03. So I reckon if we'll go 0.03 on one side and 0.03 on the other, we should be able to get the eclipse. It's probably it's symmetrical. They're not always symmetrical, but probably be the same on the other side. So 0.03 to the left, 0.03 to the right. So 0.03 of a phase, which is 0.03 times the period. So start time for the primary equals, here we can just be rough estimate, 0.3 of a phase times the period, I don't know what I did there, times the period, which is roughly that. Okay, so roughly 0.04 days before here. So if we go this minus that, and then we'll do that fudgy thing where we make it the same but we get it to show the time. So it looks like if we go from 5 AM on this time, and then I would assume that's an hour before the eclipse to an hour after the eclipse, 7, we'll capture the full eclipse. So we want to have 2 hours where we're looking at the eclipse. So we want it to go from 5:07 till 7:17. These are not exact calculations now. I'm just kind of roughing it. And that's all we need. As long as we've got the center point of the eclipse, we've kind of got most of what we need. But we'll try for this here. So I'm just thinking of the best way to do this. We can either try each time to try and get the full eclipse, or we can try and set something randomly so that it can try and get parts of the eclipse. So we could set it to take an image. Okay, I have to pause there just for a think, because this is live science. That can be my tagline for my future videos. So I've decided that we should randomly hit the eclipse, so that we'll set it to go every eclipse. We'll do a period and then a jitter, which is this wide. So as we go through this proposal, we'll get maybe an image there. I'll get a bigger button here. An image there, sometimes 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 you get the gist. But doing that, it means we're probably not going to capture the full eclipse. So while we'll have this random jitter thing, which will help us to put it together, we'll try to get one thing where it just goes down and just keeps on taking shots forever and get a full eclipse. So those random ones and the full eclipse should put the light curve together really nicely. And I'm just thinking of the best way for you to get the best light curve. I mean, with the with just trying to explain it better. If we just do the random approach where we take the period and we just get random dots all over this, most of the time the dots are just going to land in this flat bit. But what we really need is the definition of this pointy bit in these light curves. It's a different situation than you have in the other one, where no matter which part of the light curve you're in, you're going to get something varying. Here, the varying bit is in a very sharp area, and this is, you're approaching the problem of exoplanet transits. Here, if you just keep on taking images, it's always kind of obvious that things are changing, but here, most of the change is happening in a very short area. So, for here, I'm losing track of what things I have open. So for here, the first approach is the random sampling of the eclipse. So that'll be a period and a jitter starting at the point of an ephemeris. So the ephemeris, so here we've got, this is when the primary eclipse is, and then we've sort of guesstimated off the graph how wide it is, and that's about an hour. So we're going to use this primary eclipse date and put that in. There's my computer in the distance. So we want the start time to be the next eclipse, Thursday, 20th of July, 6:12 a.m. in UTC. So Thursday, and I've never pressed that clock button before. I'll do that. Do that. What a wonderful world we live in, that we can do that. Then I've lost where I am. Here we go. So 20th of Thursday at 6:12. Oh. This is the random sampling one, so it's not a big deal. And seconds, who really cares about seconds? And let's just put that a couple of weeks in the future. Let's not put it to 1 week in the future. We want it to keep on sampling till we get some stuff. So the cadence, simple period, Now the period we want here is actually the period of the object. So let's grab that. So 1 point. Probably a good idea to keep it as accurate as the value they give you. So we want this period. And then the jitter, we want it to be sampling, an hour each side, so two hours. Okay, so this will, at that time, which we've identified to be an eclipse, and then for the next couple of weeks, every time there's an eclipse we expect, try and get an image within an hour before or an hour after. Then we generate cadence and submit that. And we make another proposal for the same thing, but for the secondary. So I've described how to set the secondary period. You just add half the period. Remembering Excel date and time is all in years conveniently, and you just make another one. So change the date. It's just the date when it starts. That's the important bit. So 21, 12, etc. And then have the same thing. So you try to capture each eclipse randomly. Then at some point you will want to actually get your observations and get the full eclipse in one big 2-hour swoop. And there's plenty of time in the 0.4 meter to do each of the eclipses. But it's going to be hard to schedule because you're asking for 2 hours at once. And that's harder to schedule than asking for a random shot every now and then. So it has to wait and try to fit in a 2-hour block of time. It may be the case that we don't get it, but let's try. So here we would set the, we're not doing this cadence thing. Yes, no, let's do the cadence things, but we have to keep an eye out and make sure that if we get an eclipse, we stop it, because then we'll start eating up a lot of time. So, but what we want to do is to have the start time and when we would like the start of our observations. So we'd want to start here and then take lots of observations and then get up to there. We would, instead of 12, 10, we'll go from 5 a.m. So let's go 5 a.m. 5 a.m. Sorry. Okay. So 5 a.m. Pretty sure it's the wrong date. 20th of June. Yep. Okay, so this is an hour before the eclipse. And we want the jitter to be very small now. So you can start either, half an hour before or after. But what we'll want to do, and we're going to have to do some calculations about this, and this is probably a bit advanced. So you should probably just try and do the randomized eclipse thing. But where you get to put in the number of exposures, we'll want to do a whole bunch of exposures. So we'll get a shot, then a shot, and then a shot, 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 and keep on going through all of the filters and take lots of exposures one after the other. I feel like this is kind of biting off more than we can chew at this point in time. So I'll imagine that I'll flag that for the next time around. It is perfectly possible that using the jitter method and just getting random dots, we will define the eclipse very well. So that grand idea I just started to try and explain there at the end of this half hour, which is long enough. I'll come back to after we've got some random data from the light curve and also random data focused on the eclipse itself.